Oh, okay. I think we can sort of start. So, welcome everyone for this quantum information dynamics and non-equilibrium physics workshop at KIAS. I'm one of the organizers, Isaac Kim. Here's Zhongyan in front, and there's Hyokjun over there. So we have a pretty exciting list of speakers this week. You might have noticed the program on the website. Note that on Thursday we have a open discussion for the problem session. So if you have any ideas, like think about it, and if you want to talk about something on the Thursday, just let me know or let any of the organizers know. Okay, so we have the first talk from Robert. Unfortunately, he couldn't come because of visa problem, but he's going to tell us about this exciting work about certifying quantum states with single qubit measurements. Let's start the recording, actually. Yeah, okay. Robert, are you ready to go?
Yeah.
Okay, cool.
All right. Thank you so much for the intro. Today I'll be talking about certifying quantum states with single qubit measurements. I'll be mainly focused on the joint work with John Pascal and Mehdi Solomonifer, although I'll briefly mention at various places about some of the recent developments. So as we all know, quantum systems are very powerful. Particular quantum systems with intricate entanglements can have a wide-ranging impact across multiple different applications. For example, for quantum sensing, we wanted to create quantum systems with certain multipartite entanglement that can enhance sensitivity for detecting signals. In quantum computation, in quantum simulation, we also wanted to create quantum systems that have certain form such that we can use them for simulating physics, for understanding nature, etc. However, in the real world, when we try to create quantum system in the lab, there will always be all kinds of different noise and imperfections in the experiments that we will run into. And as a result, in order to understand if we have actually created the desired quantum system in the lab, we have to perform a task known as certification. So for those of you who have never heard of this term before, here's a very quick overview of what certification is. So in quantum state certification, we have some desired n-qubit state. So this is the target state that we wanted to create in the lab. So the psi might correspond to, say, GHZ state or a Torrico state or some other kinds of quantum states that we would like to create in the lab, which have application to sensing, for computing, for communication, etc. However, due to imperfections, due to experimental errors and noises, what we actually create in the lab would be some n-qubit state rho. So if we have done the job very well, then rho would be very close to psi. But maybe there are some errors that have happened in the evolution process or in the preparation process, such that rho is actually very far away from psi. For example, there's too much noise in the system, so rho is actually super far from psi. So the task of certification is to perform experiments on the lab state rho, and by analyzing these data, try to understand if the state rho is close to our target state psi or not. In many cases, people focus on the many-body overlap, which is psi rho psi, by checking out whether that's close to 1 or not, to discern whether we have completely certification, or to check if we have actually created a state or not. So that's the test of certification, is just to test whether a lab state, a state in the lab, is close to a target state or not. But there's one more question, which is how do we access the target state? So in general, a target state psi is an n-qubit pure state, and if we write it out, it's an exponentially long vector. Um, at the same time, there are many efficient representation that allows us to describe target state efficiently. So here we're going to consider a general access model for the target state. So we say um, we know the target state or we have some description of the target state if we assume that we can efficiently access its probability amplitude. So this is the case in a lot of different classical representation of quantum state, like neural quantum states, like tensor networks, um, or some other representation. So in all of these different cases, we can efficiently compute the following oracle, that is, given some classical bit string B, we can compute the probability amplitude, the inner product between the state B and psi. So let's say we assume this axis model. And given that this is a model that is present for a wide range of different representation of quantum state, this will be the axis model that we focus on. Of course, in other settings, in some settings, we can consider stronger models, but let's say for neural network or when we have some classical circuit representation of the state side, this is going to be the model that allows us to sort of understand what the target state is. So now we have access to the target state, and we can also perform measurements on the lab state rho. We would like to be able to complete this task of understanding if rho is close to psi or not. So many, prior to this work, there have already been a wide range of different techniques proposed for quantum state certification. But nonetheless, um, all the prior works remains experimentally challenging if the goal is to certify some highly entangled quantum many-body systems. So what I'd like to do now is to go through some of the more well-known procedures for doing quantum state certification and talk about what are some of its limitations. So let me begin with approach
Sorry,
zero.
there's a quick question.
Yeah.
But for the efficient access model you're talking about, like tensor network states, they're all kind of area law entangled. I mean,
Yes.
so I guess it's still assuming not like volume law, not highly entangled, but maybe just area law entangled states in some sense.
Oh, yeah, so for tensor network, that is the case. But if we have a neural network, then it could have volume law structure in it. Because, for example, if one just take a transformers to describe a quantum state, then the transformers can naturally embed some highly non-local computation when computing its probability amplitude. So one can imagine, indeed, for tensor network, there will be some restriction on what kind of entanglement that was in place. But if we now have a neural network model for it, then we can say, look at this bitstream B, and then just pass through some deep neural network to produce a complex number B psi. Then in that case, this can describe some highly complicated volume law entangled state. So this access model doesn't restrict entanglement in any way. Entanglement can still be extremely complicated. Another more broadly applicable, or actually in a way, one can imagine that there's just some polynomial time classical circuit that given some bitstream B can produce this complex number. And if this polynomial size classical circuit is very complicated and very deep, then this mapping will correspond to some potentially very complicated target state psi. So hope that clarifies it.
Yeah, I think he's satisfied with the answer. But one more question. What error are you assuming for this overlap? Like
So you mean like to what the
yeah, what precision are you assuming you can get this number?
Yeah, so here for simplicity, let's say we like for example for neural network and tensor network, we can just get this say exactly up to very, very small error. But I think in practice we don't need that high accuracy. I think, but then, okay, so I think as long as we can get this to a relative precision, then that's okay.
Okay, yeah, thank you. Yeah, you can go ahead. Sorry, you can't see
Yeah.
any of us, but there are like 40 people here.
I see. Okay.
Yeah,
And I'll continue onward. So yeah, so one of the approach 0 is just to directly measure it. Because what one can do is the following. Let's say we do have a state preparation circuit for the target state, in addition to the access model that I described. Then what one could do is one could just implement the inverse of the state preparation circuit, U dagger, onto the lab state, and then perform computational basis measurement. And we just check whether it returns all back to 0 to check whether the state was actually accurate. So this will work theoretically, but it's not like no one really uses this in practice. And the reason is because if we can assume that the inverse of the state preparation circuit is perfect, then in such a world, usually the state preparation circuit itself should also be perfectly implementable. So in such a world, we can just create the lab state to be the same as the target state psi perfectly, and there's no need to do any certification. So indeed, this is a theoretically sound approach for certifying quantum state, which is essentially implement a POVM measurement that correspond to psi psi and versus I minus psi psi. That allows us to estimate the fidelity. But then in practice, this approach is bogus. So I call it approach 0 because we don't want to assume we can do U dagger perfectly. Another approach is based on randomized measurements. So instead of implementing U dagger perfectly, which for some complicated quantum state, like the state preparation circuit might be some polynomially deep circuit that can be still very tricky. Another approach is to just sample a random Clifford circuit to scramble the quantum state and perform standard basis measurement. And by collecting these data, one can show that using classical shadow formalism, we can estimate fidelity accurately. So the advantage of this is no matter how complicated our target state psi is, we only need to sample a random Clifford circuit, which is of depth n, and we just need to apply that linear depth circuit onto our lab state rho, irrespective of how complicated that state is. However, the challenge, of course, here is that implementing a linear depth random Clifford circuit is still experimentally challenging, and hence that's not so desirable. However, as Tommy will be talking about in the next talk, we have this new results on generating random unitaries. Particularly, one can focus on generating random Clifford unitary in extremely short depths, in just log depths. So indeed, in that case, one can just create a log depth random Clifford circuit in order to perform this classical shadow formalism. However, the tricky bit there is that in order to run classical shadow formalism, we need to have a even stronger access model than the one described here. Essentially, we need to be able to estimate some random stabilizer state in a product with the target state, which actually for tensor network that can be quite tricky. For neural network, that's not known how to do. So if we do have that stronger access model, then we can also run this procedure. But in some cases, such as in neural network quantum state representation, we cannot run that. And another approach, which is also based on randomized measurement, is based on random Pauli measurement. So in this case, we just randomly measure each qubit in a random Pauli basis. And then again, using classical shadow formalism, we can also estimate fidelity. And the advantage of this is that we only need single qubit measurement on the lab state rho. However, the challenge is that in this case, in general, one would require an exponential number of measurements in order to estimate the fidelity. And this is true, especially when psi is highly entangled. For example, psi is some neural network quantum state that have volume law entanglement inside. Then in such cases, randomized Pauli measurements will also take an exponential number of measurements, so it's not very efficient. There's also another very popular approach based on cross-entropy benchmark, XCB for short, that was popularized by the famous quantum supremacy experiment. So for this approach, what one does is one just take the lab state, measure it all in the Z basis, look at the bit string that comes out of it, and estimate this score called the XCB score, and just try to check if XCB score is close to 1 or not. So again, the advantage is that this only needs single qubit measurement and only Z basis measurement on the state that we have created in the lab. However, the challenge is that XCB actually cannot rigorously address the certification task. It is well known, and also I will show later numerically, that there are a wide range of different situations where the lab state role can be very far away from the target state psi, despite having a perfect XCB score. And the reason is because XCB can only look at the diagonal part of the density matrix row. So if there's something wrong on the off-diagonal part, XCB will not be able to see that. And hence, if the errors is only applying on the off-diagonal elements, like some dephasing errors that happen, XCB is not going to work. So all of these existing certification protocols either require some deep quantum circuits before measurements, or require using exponentially many measurements, or only applies to specialized target state, or like in XCB, lack rigorous guarantees. And as a result, the question naturally emerges, which is, can we rigorously certify highly entangled quantum states by performing only few single qubit measurements? So here few means, let's say, polynomial number of measurements. Or if we're more ambitious, we can ask the question, can we rigorously certify almost all, or even all quantum states by performing only few single qubit measurements? So intuitively speaking, it's not entirely clear how this should be possible, because for a general quantum state, the entanglement can be highly complicated. It's a superposition of a bunch of different things. So if we now only perform some single qubit measurement, they're just measuring things locally. So intuitively, it felt like these local measurements shouldn't be able to enables us to see these long-range entanglement that are present in the quantum state. So a priori, it's not clear that, or it's not even intuitive that we should be able to certify some highly entangled states by performing few single qubit measurement. But as I will show in the later part of this talk, actually the answer to this question is yes. So the outline of my talk is as follows. I will start out by stating the theorems, and then going through the protocol, finally ending with applications. And towards the end, I will also talk about an exciting new progress that was made by Ryan O'Donnell and students at Berkeley and CMU that made progress to answering one of the major open questions in our previous work, in this work. So let me begin with the theorem. So the first theorem that we show in this work is that for almost all n-qubit state psi, so any target, for almost all target state psi, we can certify whether the lab state is close to psi or not using just a quadratic number of single qubit measurements. So note that this certification protocol applies to any lab state role. So no matter what the error is, even if it's highly adversarial, we can see that. And furthermore, no matter how complicated the target state psi is, even if it has exponential amount of circuit complexity, just a quadratic number of single qubit measurements is enough to perform certification. So that's the first theorem that we establishes. But then one would ask, what about what if I have a very specific target state psi? Then does it apply to this theorem? Can we also efficiently certify that specific target state psi? So in order to understand that, we look at the following. So consider an n-qubit target state psi. So it's an arbitrary target state. And let's say we choose some basis B. And now we define pi of B to be the measurement distribution. That is, if we measure the target state psi, according to this chosen basis, what is the measurement distribution that appears on here? So just to visualize it, one can imagine that we have this Boolean hypercube corresponding to a 3-qubit target state psi. Then this measurement distribution will be some distribution over these 8 vertices. And now let's say we consider a random walk on this n-bit Boolean hypercube. So let's say we start at this point. So let's say the Walker state start at a bit stream B, correspond to here. Then what the random walk would do is every time it will choose one of its random neighbors. So in this case, there are 3 different neighbors that I can choose from. Let's say it chooses 0, 0, 0 as its neighbor, so B prime. Then this random walk is defined pretty naturally as follows. The walker will either just stay at its original place with a probability proportional to pi of B, or it would jump to its neighbor, B prime, with probability proportional to pi of B prime. And it would just keep walking this way. So every time it will look at one of its random neighbor, and then with probability proportional to pi of itself, it will stay. And with probability proportional to pi of its neighbor, it would jump to that neighbor. So just keep walking on this n-bit Boolean hypercube. And eventually it will converge to this measurement distribution. And we define the time, tau, to be the time for which it relaxes to the stationary distribution, tau, pi. So pi is the measurement distribution defined by psi. And because we have designed the random walk according to this measurement distribution, if we just keep applying these random walk update, then in general, it will just converge to the stationary distribution. So we call tau essentially the tau is also known as the relaxation time. And basically we can prove the following theorem, which is for any n-qubit state psi that has a relaxation time tau, we can certify whether the lab state rho is close to psi using only order tau single qubit measurements. So as long as the relaxation time is not too high, then we can certify them efficiently. So in order to reduce back to theorem 1, essentially what we proved is that for almost all state psi, its relaxation time is bounded above by n squared. And hence, we have theorem 1, which states that for almost all n-qubit state psi, we can certify them using only order n squared single qubit measurements. But more generally, it actually depends on what is the basis that we choose. And with respect to that basis, what is the measurement distribution that we will get when we measure that state with the basis. However, what we showed is that if we just pick, say, the standard basis, the standard computational basis, now for almost all state psi, this pi of B will be rapidly mixing and has a very short relaxation time that is of order n squared. And that's how we establish theorem 1 from theorem 2.
I have one question.
Yeah.
So then the goal is finding a basis where the relaxation time is like optimal in some sense.
Yeah, one could think of it that way. Or in a way, one could say, okay, suppose I have some target state psi that I care about. Let's say GHG state. So GHG state, if I consider the standard basis, then it will be supported on the two kind of two end of this hypercube, which is kind of highly disjoint and not rapidly mixing. But in that case, we can say choose the basis to be all X basis. So we measure everything in X basis. Then actually it becomes highly spread out, and then it becomes rapidly mixing, and we can actually certify such states with just order n single qubit measurement. So indeed, if we have some target state psi, one could, for example, try to find a good enough basis such that it becomes rapidly mixing. Or, but actually, in general, which is what this theorem essentially says, is that generically, when I just pick some state psi, as long as I'm not too fine-tuned, then the state will be rapidly mixing, and hence this measurement distribution is highly spread out, and the relaxation time is upper bounded by n squared, and so we can certify them efficiently. However,
Oh, sorry, keep going.
no, go ahead.
So, given a state psi, how can we find the optimal? Is there like polynomially efficient procedure to find the optimal basis, or if we just pick any random basis, it's almost surely a relaxation time would be given as like n square.
Yeah, so actually, yes. So optimally, I don't actually know, but it is true. Like essentially what this first theorem says is that if one just picks some random basis, then indeed for that random basis, it will be because one can kind of like shift the randomness. So here, essentially the proof that we showed is that given a fixed basis, if I consider some random state, generically it will be rapid mixing, but one can do the same thing. So if we pick a adversarial worst case state psi, if we pick a random basis, that would also be rapid mixing. So both are true, even though I'm stating theorem one in one way. But this might not be the optimal one. For example, maybe the optimal one can achieve only just order n single qubit measurements, which will be even more favorable. Let's say I have 10 to the 4 or 10 to the 5 qubits. Then in that case, order n squared is still a little bit too high. So perhaps in those cases, I would like to optimize it to get order n. However, right now it's not clear how to um, choose the optimal basis to guarantee that this measurement distribution is pretty spread out and have good relaxation time. So I would say that's still an open question. However,
One last,
yeah, go ahead.
sorry. Well, one last question. If you can transfer randomness from basis to state and state to basis when everything is random, but if you limit your basis to be a Pauli, well, I guess you stated something.
Yeah, you mean like let's say if I limit our basis to just be Pauli basis, then yes, then in that case it's no longer clear. However, I do want to mention there's which I also talked about towards the end, but there's this very nice work that just appeared last week that shows that for any target say psi, there's always a way to choose a single qubit basis, meaning like a local basis. Just let's say for the first qubit we choose something and then so on. So there's always a way to choose a single qubit basis such that this measurement distribution is rapidly mixing. And then they call that a decision tree basis. That's a recent paper by Ryan O'Donnell. So there is way to play more trick or have more kind of innovation on the basis choosing part, and
Thank
that
you.
could really help the certification procedure. So for example, if I can find a basis such that pi of b is just a uniform distribution, then in that case, the relaxation time is known to just be order n, so linear in system size. In that case, we only need a linear number of measurements in order to certify the state. So yes, but how to optimally choose the basis? I would say still an open question. But as long as one can do that, then this can be one can always certify. And there's also kind of a different version of theorem 2, which states that if we now restrict not just to single qubit measurement, but to restrict it to independent Pauli basis measurement. That is, I would always just be measuring in some Pauli basis. Then in that case, one can also show that we only need order tau squared single qubit measurements in order to certify the quantum state.
Yeah, I think you can go ahead.
Yeah. So let me So after stating the theorem, let me go through what the protocol looked like. It's an extremely simple protocol. We just simply repeat the following for a few times. So you have some quantum state, the lab state that we created in lab. What we do is we pick a random qubit X, so one of it chosen randomly. And then what we would do is we will measure everything else other than that chosen qubit, everything else in the standard Z basis. And then for that chosen qubit, we will measure in a random XYZ basis. And that's it. We just keep repeating this for a few times to collect data from here. And using these collection of data, we can certify the states. So the post-processing looks like this. So note that every time when we perform a measurement, let's say we have chosen some qubit X, and then we perform Z-basis measurement on the rest of the qubit. This what the measurement outcome of these Z-basis measurement, it always specifies essentially two bit strings, corresponding to either getting 0 for the chosen qubit or getting 1. So we can imagine that these rest of these qubits specify these two bit string B0, B1 that differ by exactly 1 bit. So just to be more concrete, let's say we have a 3-qubit system and we choose the middle qubit to be qubit X. And then we measure the remaining 2 qubit, and let's say we get 0 and 0. Then in that case, it will specify this edge corresponding to 0, 0, 0 versus 0, 1, 0. So every time when we do one measurement, this is what we get. So now suppose that our target set is psi. Then in the ideal case, the post-measurement 1-qubit state, that is, after we measure out everything, the post-measurement 1-qubit state on this qubit X will be proportional to this. And we call that psi B0, B1. So it's just B0 psi, and then 0 here, plus B1 psi, and then 1 here. It's proportional to this, and it should be properly normalized based on the probability amplitude associated with B0 and B1. But that's the ideal case. In the lab, we actually don't know. It just corresponds to some random single qubit state that just appeared here. However, note that this ideal post-measurement 1-qubit state can be computed efficiently, assuming this axis model that we described. So if we can just given 2-bit string B0 and B1, we can estimate these complex number efficiently. Then we will be able to figure out what this ideal post-measurement 1-qubit state is. It's efficiently computable using this axis model that I described, which is available for neural network quantum state, tensor network states, and various other representation of quantum states. And now what we do is we will use this single qubit one-shot randomized Pauli measurement, this classical shadow on this qubit X, to predict the fidelity with respect to the ideal state. So note that after we measure everything out in the lab, we will just get some 1-qubit density metrics here that is actually conditioned on the rest. Because depending on what we get on this measurement, this will be different. And in general, it would always be different because we will get different bit strings for the rest of a system every time. We can never really post-alike on things, so it's just always going to be different. We'll just get different things. But no matter what we get, we can always calculate the ideal 1-qubit state and use the randomized Pauli measurement and classical shadow formalism to estimate and to predict the fidelity omega with this ideal state for this. So essentially what we're doing is we're just kind of first measuring out everything else, and now looking at that kind of post-measurement state and just estimating the fidelity. And now if we average over all of these different single qubit fidelity omega, we get this quantity that we call the shadow overlap.
Robert, quick question about this.
Yeah.
So when you measure everything but 1-qubit,
Yeah.
and then you're left with one like post-measurement state,
Yeah.
but you only get like one sample of that, right?
That's
Like
right.
how do you estimate the fidelity from like, because like you can't get the same post-measurement state as you want, right?
Yes.
So how do you get the the single qubit post-measurement state fidelity?
Yeah, that's a great question. So we are not really, we can never really get the true fidelity, but we can get an unbiased estimator. So which means we can get an estimate such that that estimate has an expectation value equal to the true fidelity, but then it has a large variance. So there will be a variance. So for example, we just get some random number that fluctuates around it. However, we're going to just average over everything. So we're going to average over the choice of the qubit X that we selected. We're also going to average over the measurement outcome for the other qubits, and then also average over the kind of the internal randomness. So here this E of omega corresponds to averaging out all of them. So indeed, for each individual one, because we only get one shot, we only get one measurement, we can never see that fidelity very accurately. There will be a large statistical fluctuations around it. But now but if the goal is just to get the average over all of these things, then we can actually get that final average, which we call the shadow overlap. So this expectation value, we can get to very high accuracy because we're just going to keep repeating the same kind of independent random procedure over and over again. And then we can use standard concentration inequality to show that it concentrates to this expectation value because the variance is always a constant.
Okay. Yeah, thank you.
Yeah. So what is the key feature of this quantity that we just newly defined? So the key feature is that this shadow overlap actually accurately tracks the fidelity. In the sense that if this shadow overlap is close to 1, that implies that the fidelity is close to 1, up to a slackness. And here the slackness corresponds to this relaxation time that I described. On the other hand, if the fidelity is close to 1, then it also implies that the shadow overlap is close to 1. So this means that by checking whether the shadow overlap is close to 1, we can know whether the fidelity is close to 1. And hence, we can just look at the kind of the average shadow overlap in order to see if it's close to 1 to identify whether the lab state is close to our target state or not. So more broadly speaking, we can also just write out this shadow overlap here. The first average corresponds to which is the qubit that we're choosing, like this random qubit X that we're choosing. And then this sum corresponds to the measurement outcome for all the rest of the qubit except for the chosen qubit. And then this expression shown here corresponds to the probability for getting these B not equal to I multiplied by the single qubit fidelity. So shadow overlap corresponds to this, and using standard concentration inequality, we can show that we can get shadow overlap up to a small error just by averaging all of these experiments. So one can get some intuition by plugging in a few different states. So suppose the lab state is all plus and the target state is all minus. In this case, the fidelity, as we can see, is 0. And if we plug in these two states into the expression above, we can see that the shadow overlap is also 0. On the other hand, so in this case, both of them matches. But there are cases where they can actually diverge. So they can actually be quite different. So here's one example. So if the lab state, or if the lab state is all minus, but the final qubit is plus, but the target state is all minus, in this case, we can see that the fidelity is still 0. However, when we plug these two states into the expression here, one can calculate it and show that this actually gives a shadow overlap that is n minus 1 over n, which is not 1, but also not that close to 0. So as we can see, like and actually more broadly speaking, if there's k qubit that are plus here, shadow overlap would be n minus k over n, whereas fidelity is always 0. So what this means is that while shadow overlap has this feature that it kind of tracks fidelity, it doesn't exactly matches. It
I
doesn't
have a
exactly
quick
match. Yeah.
I have a quick question. So here the calculation is assuming the computational basis is a plus minus.
Oh, no. So here it's assuming that here it's still the normal computational basis, but the state looks like this.
I see. But if you choose plus minus basis, then would you get different shadow overlap?
If one chooses plus minus basis, then yeah, so changing basis sometimes changes the shadow overlap. But in this case, I think it's still going to be fine, but it might still be the same, but one
Okay.
should double check it. Sometimes changing basis changes this. That's a good question. But overall speaking, because shadow overlap is just looking at one qubit at a time, it has more of these Hamming distance flavor to it, compared to fidelity, where if one of the qubit is off, then things are off. Okay, so after talking about the theorem and the protocol, let me dive into the applications. So, what can we do with this new certification protocol? So as indicated by the initial motivation, the more obvious application of this is to perform benchmarking, because by checking shadow overlap, one can certify if the state has high fidelity or not. So for this part, let me show some experiments when comparing with cross entropy benchmarking. So here, this is a result when I consider 4-qubit Haar random state as the target state and only subject to white noise. So the white noise regime is a regime where XCB is known to perform very well. And as one could see here, as the white noise increases, the true fidelity start going down, shadow overlap also start going down, and XCB also start going down. So this part, everything is good. However, if we now look at having only dephasing noise instead of white noise, so dephasing noise just kind of changes the off-diagonal part, then in this case, XCB start to fail pretty badly because it has no way of identifying errors that happens on the off-diagonal parts of the density matrix. So as dephasing noise increases, we see that XCB still reports a perfect score, whereas the true fidelity start going down and the shadow overlap start going down. So one thing to note is that in the low noise and when the noise is pretty global regime, then shadow overlap can track true fidelity quite well. But eventually it has to deviate because as we have talked about earlier, shadow overlap can deviate from the true fidelity. So in this case, in the large noise regime, we do see that they're slightly different because in a way they're a different quantity. They track each other only when the noise is small and the noise is pretty global. Here's another example when having coherent noise. So in this case, we can see that XCB look like this, whereas shadow overlap tracks the fidelity more accurately. This is another experiment, but focused on random structure state. So we consider some product state subject to some random phase. In the white noise regime, we see that XCB has a good expectation value, but has a much bigger variance. So we're comparing between having the same number of measurements, and we see that XCB has a very large statistical error, whereas shadow overlap has a error that is much, much smaller. And the reason is because in the XCB calculation, one has to divide by the collision probability, and that collision probability can become, if the collision probability is, or depending on what the collision probability is and how it's fluctuating and so on, the variance of XCB calculation can change quite dramatically. Here's another example. Under dephasing noise, again, we can see that XCB fails to detect any errors when we are subject to dephasing noise. Now here we consider having coherent noise in the lab state, and we see that XCB is behaving in a quite strange ways. As the coherent noise increases, somehow it start reporting a a score that is above 1. So note that it's quite well known that XCB only works under the white noise approximation. So whenever one deviates away from white noise, then suddenly the behavior can be pretty crazy like this. This is basically the same experiments, but for 12-qubit system, we can see similar feature like dephasing noise. XCB is behaving strangely. Incoherent noise is also behaving in a unpredictable way. This is for 20-qubit, also similar feature. But yeah, the overall XCB and shadow overlap rely on essentially the same access model. So we need to be able to estimate probability amplitude efficiently. And yet, shadow overlap tends to perform much better compared to XCB just by measuring 1-qubit in a non-Z basis. So XCB measure everything in Z basis and then calculate XCB score. But if we have the capacity to measure one of the qubit in a random XYZ basis or in XY basis, then suddenly one can perform benchmarking much, much better compared to XCB. So that's one application of performing benchmarking. A different application is one can also utilize it for certifying models of quantum state. So for example, in neural network tomography, the idea is that we will try to train a neural network to represent some quantum state in the lab. So in the lab, we have this lab state role, and now we would like to train some neural network representation so that we can see what's the state in the lab. However, a priori when people utilize neural network or people try to train neural network to learn quantum systems, they can hallucinate quite badly. So there's no good way for justifying or for certifying whether the neural network representation accurately captures the lab state or not. However, utilizing this new certification protocol, we can essentially repurpose them to certify these ML models. So just to kind of provide a quick recap. So in the standard neural quantum state, one represents a pure state psi as follows. So we consider a neural network such that when we put in some classical configuration, it can spit out the probability amplitude. Here we consider a slight variant of it, which we call the relative neural quantum state, where we give 2-bit strings that differ by 1 bit, and then the neural network will essentially spit out the relative amplitude between the two. And note that in this case, it can also represent the pure state psi because we can use the neural network multiple times and just by simply multiplying all of these relative amplitude in order to get the probability amplitude of the state psi. And here we consider learning a class of 120-qubit states with extremely high circuit complexity. So because this one can just set up some random neural network, as long as the neural network is quite deep, then it can effectively represent various volume law entangled state. And because the quantum state is volume law entangled, we would expect that the purity, the subsystem purity, will have to decay exponentially. And that is what is being plotted by this dashed line shown here. So if we look at the subsystem 1 through I, then the subsystem purity of a volume law entangled state will decay exponentially from 1.0 to 0.5 to 0.25 and so on. On the other hand, when we randomly initialize this neural quantum state such that all of its weight is very close to 0, then it will start out representing just a trivial state with no entanglement inside of it. So we see that it looks like this. And now we can start training them. So the idea is that we will use the shadow overlap that I described as to define a loss function that we can effectively use to train the neural network. And furthermore, we can use, again, shadow overlap to certify the neural network. So prior to this, people actually don't know how to check whether the neural network that was trained on the classical computer actually matches the lab state. But now one can essentially utilize this same procedure that I described to check whether that's true. And here's the training dynamics associated with training a neural quantum state to learn some unknown quantum system. And here we can see that the loss function start originally it's just randomly walking. And after some time, it figures out the right pattern and it quickly decays onto a small loss function. So here it's a log loss function based on the shadow overlap data. However, at this point, it's not clear that the neural network actually has learned it or actually has got stuck in some local minima or it got stuck in some barren plateau. However, we can easily distinguish all of these cases by just looking at the shadow overlap. So as we can see from this other line here, we see that after training it for sufficient number of stochastic gradient descent steps, the shadow overlap is now very close to 1. And we can also see that the true fidelity is also very close to 1. And as a result, we know that the neural network has actually done well in learning the state. And furthermore, using the theoretical guarantee, we can certify that the neural network is now a good representation of the unknown quantum system in the lab. And hence, we can start using the neural quantum state to predict all kinds of different properties of the quantum system. So here we showcase the result for predicting subsystem purity using the trained neuron quantum state. And as we can see, it matches with the ground truth very well.
One quick question.
Yeah.
So can you go to the previous slide?
Yes.
So if the fidelity is already like, so here when you show the star fidelity, it's exact fidelity between the trained state and the target state?
Yes. Mhm.
So when that happens, when it's exactly close to 1, why is loss still significant? Why isn't it extremely tiny?
Yeah, so it's because log loss is log is more like one should think of it as log loss at the end. Okay, so in this kind of training these probabilistic models, the log loss just corresponds to trying to match the probability distribution. So in the setup, the log loss is defined as like the log of the probability for the data that we see, based on the model that we have. So we will just be estimating what is the probability of seeing a certain data point, associated with the model that the neural network is producing, which even when one minimizes it, there will still be an inherent entropy because it's at the end it would just be the entropy of it. So the log loss doesn't really decay all the way down to 0, which is a common feature in a lot of these kind of generative models that people are training. Like one would just be kind of trying to match or trying to minimize the log of the probability, or
Okay.
people call the log likelihood. So the optimum point of log likelihood is not necessarily 0 because or it cannot be 0 if the distribution has some entropy inside of it. So that's why the log loss cannot go to 0 because when it goes to 0, it means like it has no entropy.
Okay.
And yeah, so in a way, in a lot of these generative modeling, which in some sense this is what the neural network is doing. It's like it's trying to mimic the probability distribution for which the data that we see. So we have a state in the lab and we perform measurements. We now see these measurement data, which we then use to train the neural network. So kind of the training loss is that we wanted to train the neural network so that it matches the probability distribution for which we see the data point. And so it's inherently a generative model. And in these generative models, what we can see are these log losses, which yeah, they will be saturated by a certain number depending on the entropy of the unknown distribution that is trying to learn. And as a result, and if one just look at this log loss, like you're saying, actually there's no way to tell. It could be that this 0.35 number corresponds to some bad local minima. And in that case, when we estimate shadow overlap, we will see, because we'll see that, oh, actually the shadow overlap is like 0.5, which means this is wrong. So a priori, like before all of these, we can actually not tell whether we have succeed. And note that here, in experiments, the fidelity is not known to us because estimating fidelity directly is very hard. It requires some deep circuit or requires some other complicated things. So the fidelity is not known to us. It's known here because we already know what is the unknown state, but in practice we don't know. All we can estimate is this shadow overlap line. However, as long as we see that the shadow overlap is close to 1, then we know that the state has trained well, even though like the log loss will look like some weird number like 0.35. Okay, so yeah, so the another app, just to in light of the time, another application is in optimizing circuits. So in this case, suppose the goal is to prepare a target state psi. Then what we can do is we can try to optimize the circuit, the state preparation circuit, to try to maximize the state shadow overlap. So one thing I wanted to note here is that if one just uses normal fidelity to try to do the optimization, we will run into barren plateau, because only until we have almost successfully constructed the target state, the fidelity will tell us that this is 1. Before doing that, the fidelity is going to be very, very close to 0. On the other hand, when we utilize shadow overlap, it has this more of this Hamming distance nature to it, and as a result, it would give better training signal. So here, this is the result when we train to prepare some 50-qubit matrix product state using a Monte Carlo optimization. We can see that if we train it using shadow overlap, the shadow overlap score will keep rising and rising until it saturates. Whereas if we train it using fidelity, it would just be kind of randomly walking in this barren plateau and doesn't really improve. And if we look at fidelity as the metric over the kind of the training duration, we can see that when we train it with shadow overlap, the fidelity is very close to 0 for most of the time, until the shadow overlap is now very close to 1, which is suddenly shoots up and becomes a fidelity of 1. On the other hand, if one just train it with fidelity, then the fidelity will continue to remain 0 because it's randomly walking on this barren plateau. So to conclude, we proved that for almost all quantum states, one can efficiently certify using very few single-qubit measurements. And one of the main open questions that we raised in our previous paper is that whether one can actually certify all quantum state with few single-qubit measurements, because our result only applies to certifying almost all rather than all. And so I wanted to give a shout out to this exciting new development that just happened last week by Gupta, He, and Ryan O'Donnell, where they showed that if one assumes a stronger access model, that is the ability to be able to compute the inner product between the target state psi and any product state phi. So this is this access model is available for things like tensor network and some other representation. But for neural network, it's not clear. So neural network, it's not clear how we can estimate this. And actually, there are known cases where there is some neural network that one can estimate B psi. So for standard basis B, like a bitstream B, one can estimate the inner product efficiently, but estimating the inner product between a product state and psi is going to be computationally hard. Like this IQP circuit is one such example. However, if one assumes having access to the stronger model, then actually one can show that one can essentially utilize this access model to find a basis such that for under that basis, the measurement distribution is rapidly mixing. It's essentially uniform. So if one just measure in that basis, which they called a decision tree basis, where they kind of essentially generate that basis by continuing accessing these stronger access model, one can certify all quantum state efficiently using, again, order n squared single qubit measurements. And that's it for my talk. Thank you so much for listening.
Okay, thank you for the very nice talk. We have some time for questions. Oh, lots of questions. Okay. Well,
Hi. Yeah, thanks for the talk. So my question is about, so in your access model, you're assuming you have access to the amplitude. So is it important that you have access to the phase, or would the square suffice? I didn't get this, or where does it come in?
Yeah, it comes in at this one step during the post-processing, which is here. So we essentially need to be able to construct this post-measurement one qubit state. So if we have some n-qubit state psi for our target state, if we now measure n minus one qubits in the Z basis, we wanted to be able to efficiently compute the one qubit post-measurement state in the ideal case, in the target state case, which is proportional to this state shown here. So this is our normalized state. And so in this case, it's efficiently computable if we can estimate the probability amplitude efficiently, which includes both the magnitude as well as the phase.
Thanks. Yeah.
Yep.
Yeah, I have just a simple general question. Do you know if efficient certification protocols all require the ability to make simultaneous measurements on all of the qubits?
Oh, you mean like suppose I can only measure a subsystem and then every time I can measure part of it, but then not seeing the rest, then could we
Right.
still efficiently certify the quantum state?
Yeah, is there anything known about whether that's a no-go?
So there are sort of like trivial examples where it would not be possible. Let's say my target state is a hard random state or some highly entangled state. Then if I only measure, say, half of a system, it would always effectively be completely mixed. So in that setting, one definitely would not be able to certify whether the full state is good. But if one can maybe look at some random subsystem and maybe there are certain patterns, some more restriction on the target state, then maybe there's some possibility. But yeah, but I don't. But at least immediately come to mind is that when I just have some highly entangled state, if I look at subsystem, it will be concentrated and as a maximum mixed state. So we will not be able to get any information out. But if one deviates away from that, how things would look, I don't really know.
I had two questions about this random walk on the hypercube.
Yeah.
One is, if I understand correctly, there is a gap between this order n squared mixing time and the kind of rapid mixing case, which would be n log n. Do you think that's real, or is there just a question of what you can prove? And also, is there some connection to this kind of cutoff phenomenon that you have on like random walks on hypercubes?
So in terms of theorem two, if let's say the distribution is just uniform, then this case tau would be n, and then theorem two actually gives one order n. So if one does have these like strongest rapid mixing, then the number of measurement is indeed just linear in system size rather than quadratic. However, in theorem one, as we have n squared, and also in Ryan's new paper from last week, they also have n squared. Um, I don't yet know if one can, I feel like it might just be an artifact of the proof strategy. Because in this case, what we're trying to do is we are trying to essentially, or in a way, what we are proving here in theorem one is that if we now have a generic distribution coming from Porter-Thomas distribution, then such a generic distribution will always be rapid mixing, and the mixing time is always bounded above by n squared. But it could be that it's much closer to like n log n. Right now we're doing these kind of big cumbersome like multi-commodity flow in order to estimate or in order to bound the mixing time. But I don't know of any lower bound that says n squared is necessary. So there is a gap between n squared and n, and I think understanding that gap could also be important question if we're really thinking of kind of certifying some very big system like 10 to the 5 qubits, which people are building in the lab.
Hi, Robert. You show a neural network model learning the quantum state using the shadow fidelity. So is there any limitation of this learning? Like, does it depends on the underlying state you are trying to learn? I thought maybe it's not possible for neural network to learn all kinds of quantum states using this approach. Otherwise, I can always come up with a model that learns the distribution and then try to cheat your certification procedure to let you think that I really have the quantum state in my hand, although I just have a classical AI model in my hand. Is there any? Yeah.
Are you asking more about so first
Like I didn't prepare the state, but I can cheat you that I really have the state you want to certify. I don't have even a quantum device. I only have an AI model that can respond in the similar way that that tells, for example, that produce this shadow measurement outcome condition on the other qubit measurement outcome. So if I have that classical model, I can actually cheat your certification process to let you think that I actually has prepared the quantum state that you want to certify, although I just have a classical AI model in my hand. So I thought it cannot be possible for all kinds of quantum states. There are quantum states you really need to prepare. You cannot use a classical model to cheat the certification procedure, right?
Yeah, that's a great question. So actually, if one can, for example, like if one can simulate these entire measurement protocol that was described here classically, then yes, then one can cheat. For example, if I have just, let's say I wanted to cheat that I have GHG state, then GHG state is a stabilizer state, and all of these measurements are just stabilizer measurements or Pauli measurements. So indeed, for those cases, I don't need to intrinsically create a quantum state in order for these procedure to hold. So in that sense, yeah, this is not a proof of quantumness in the strongest sense.
But I think there are quantum states that are intrinsically very difficult to simulate. And then even for classical AI model, you can't actually predict the XYZ measurement outcome condition on the other qubit, right? So for those quantum states, probably.
Yes. So indeed, for those, then it will not be, it will be not possible to cheat. One would definitely have to use a quantum computer to do it. I think one example is this like random phase state. If I have a uniform superposition, but the phase is random, then for those kind of systems, then it will be very hard to cheat this. And indeed, that also implies that for those kind of neural quantum, there will be states where the neural network cannot represent, at least under reasonable complexity theoretic assumption. Neural networks will have a boundary for what kind of states it can represent. So going back to this specific case, there are a lot of criteria that need to be met. For example, first, the state psi needs to be representable using a neural network. So that's one. And then that's not enough because then one also need to have a good landscape. It's not true. Yeah, like here we didn't prove anything about landscape. So the landscape needs to be good enough such that one doesn't get stuck in some weird local minima or the landscape is very hard to navigate. So the landscape needs to be good enough for the neural network to learn. And then, but after if these two conditions are met, then finally one can utilize the shadow overlap to certify it, that one has truly learned it. So indeed, it doesn't, one cannot learn any possible quantum system. We don't expect that to be the case. And there will be states that will be very hard to learn or even represent with neural networks.
There was a question.
Thank you for the nice talk. How do you think about performing a certification task using classical shadow with states forming an approximate 3 design and having polynomial number of superpositions, if it exists?
Sorry, could you say again the last part?
Performing a certification task using a classical shadow with states forming an approximate 3 design and having supernomial number of superpositions. So for that case, even with your access model, we can perform classical shadow with polynomial time, I think. So how do you think about such scenario?
Oh, you mean like comparing between our like random Clifford classical shadow versus using this approach?
Not random Clifford, but if there exists such an ensemble of states that forming an approximate state 3 design, which is necessary condition for the classical shadow to be efficient, and having a polynomial number of superposition so that you can estimate the shadow, shadow estimator in polynomial time.
Oh, you mean like how do they contradict each other, or was that the
So for the case, you can I think you can estimate a fidelity in polynomial time with logarithmic depth quantum circuit.
Yes.
With number of samples proportional to 1 over epsilon square with the accuracy epsilon.
Yeah.
So how do you think about this protocol compared to your shadow overlap?
Yeah. So for that setting, of course, one need to implement log depth quantum circuit so that whereas here it's just really Pauli measurement. So in that sense, the experimental requirement is much simpler here. So I would say that's one of the difference. And yeah, so I would say that's one of the difference. I mean, in that specific setting, that's one of the main difference for the comparison. But at the same time, if one does get the ability to perform these low depth quantum circuit, and one can do that pretty well, then I would say that could be better because it only requires over 1 over epsilon square measurements, whereas here one would require more number of measurements, at least let's say linear in system size. So there is a trade-off between how many measurements one is doing, but of course there's also this trade-off between how many quantum gates one needs to apply in doing so. So
thank
you.
Yeah. Maybe one last question. Yeah.
Thank you for the great talk. Your main statement is about applicable to almost all quantum states. And could you be more specific about the exceptional states? Do you have concrete example, or what's the limitation of your method?
Yeah. So as long as if we one goes back to here, as long as one can, let's say there's a state, as long as one can find a basis B such that the measurement distribution on that basis is rapidly mixing, then those states will be applicable with this procedure. And essentially what this recent paper shows is that for any target state psi, there's always these decision tree bases such that when one measures according to that decision tree basis, the measurement distribution will be uniform. So that's why any quantum state can be certified using just few single qubit measurements. But of course that requires this decision tree basis that might be a bit challenging to find. So in this case, more specifically, I would say almost all state that one tries to write down, it's really going to have this rapid mixing behavior. So for example, if one writes down some W state, that is rapid mixing. If one writes down GHZ state, if you measure in the X spaces, that's rapid mixing. If one writes down, say, the ground state of some gap Hamiltonian, that's also rapid mixing. If one writes down, say, a uniform superposition over all possible classical or all possible classical bit string, but the phase is arbitrary, all of them are rapid mixing. So there are indeed all of these different examples that was laid out in the paper, where the rapid mixing condition can just be shown kind of precisely.
Yeah, so thank you for clarification.
Yeah, no worries.
Okay, so I'm gonna have to stop now. So thanks everyone for, well, thanks Robert for a great talk. Let's give him an applause one more time. Yeah, yeah. So